something colossal is rising from the Texas plains. A $50 billion microchip factory. One of the most expensive and complex projects in the US history. And this isn't just a factory. It's America's front line in the global chip race. On paper, this new facility is a marvel. Built to rival TSMC's new mega factory in Arizona, just one state away. But before it even came to life, it's already failing. I'm an engineer who spent over a decade in semiconductor industry. And this story is unlike anything I've ever seen. And everyone should understand what's happening, because the future of AI and entire global economy depends on it. To understand why, we have to go back to the company behind it, and the moment when it's almost conquered the chip world. A decade ago, Samsung was unstoppable. It was, and still is, the second largest chip maker on the planet, and the only one still keeping pace with Taiwan's TSMC. Their dominance in memory chips is nothing short of legendary. From DRAM in every server and smartphone, to NAND that stores the world's data. And memory wasn't enough. They also built logic chips, the brains behind the first Apple iPhones, NVIDIA's early GPUs, and Tesla's first autopilot computer. By 2015, Samsung was on top, mastering 14nm process, landing Apple, and standing right behind TSMC. For a moment, it looked like they might even overtake them. But then everything turned. Apple became direct rival, and trusting Samsung to build iPhone chips was literally like asking your enemy to sharpen your sword. So Apple left, moving all chip production to TSMC, a foundry that built chips for everyone but competed with no one. Then came the cracks from within. Unlike TSMC, Samsung was pulled in every direction, building chips, building memory, but at the same time displays and smartphones. Their 10nm process slipped behind schedule. Yields crashed. By the time TSMC ramped 5 and 3nm production, Samsung was still fixing 7. Yields fell to around 40%. NVIDIA walked away. Then Qualcomm. Then Tesla. Each loss drained billions of dollars and confidence. And it wasn't just the logic side that struggled. Memory business was shrinking too. Micron and Xilinx kept taking a bigger piece of the pie. And that's when Samsung decided to do something no one expected. Rebuild its chip empire, but on the other side of the world. In 2021, they decided to build a $17 billion chip factory, not in Korea, but in the heart of Texas. A factory so ambitious, it was announced as the most advanced semiconductor factory ever built on US soil. The company chose Taylor, a quiet town northeast of Austin, far away from Pyeongtaang, but close enough to its biggest customers, NVIDIA and Tesla. The mission was clear: prove that advanced chipmaking could thrive in the US again. And Taylor was a perfect choice. Close to Tesla, Qualcomm, and Google, and surrounded by a booming tech scene hungry for AI silicon. Even the land itself seemed made for it. Vast, flat, and geologically stable, far from earthquakes or floods, with almost zero risks of natural disaster. And that's perfect for massive clean rooms and billions of dollars in equipment. On paper, the plan looked simple. Break ground in 2021. Start 4nm microchip production by 2024. And then push toward 2nm soon after. This Taylor fab promised to make a history. But unlike the other Taylor, this one can't quite hit the right notes. Honestly, it's kind of insane to tell the story, because whatever could go wrong went wrong. And here is where the story gets truly insane, because building a chip factory isn't just pure engineering, it's choreography at the atomic level. Imagine you are about to build the most advanced chip factory on Earth. And here is a twist. You don't start with concrete. You don't start with machines. You start by locking in the direction. Step 1, lock the node, the transistor generation your fab will produce. And lock the first customer, the company whose chips you will build. And that first customer is very important, because the chip design of the first customer is how the fab calibrates and optimizes every step in the process. And that first step defines everything that follows: the tools, geography, recipe, floor plan, even the power grid, the entire playbook. First, Samsung decided for 4 nanometers, a safe, mature node, solid yields, known recipe, and predictable economics. But just as construction began, the world hit fast forward. AI workloads exploded, and every major chipmaker started chasing 3 nanometers and below. TSMC was already ramping up Apple and Nvidia chips on its newest process. And Samsung didn't have an anchor customer of that scale. And here Samsung made a fateful decision: pivot Taylor to 2 nanometers. It sounded bold, but in reality it was catastrophic. And that single change turned a controlled build into a pure chaos. It meant new tools, new recipes, and steep learning curve. Even in Korea, Samsung was still struggling with this node. And the math blew up overnight, because moving from 4 nanometers to 2 isn't just about swapping a couple of machines. It means reinventing the entire factory. The original $17 billion plan ballooned to $50 billion. This change pushed the schedule out and the budget through the roof. And that was before they even broke the ground. Because before you even start building the walls, you have to conquer the earth itself. The soil under Taylor looks calm from above, but it's not. It's calichy, hard, dry, and uneven. Strong enough to hold a highway, but not stable enough to hold the semiconductor fab still. When you're printing transistor features smaller than a human eye can see, even the tiniest vibration can destroy everything. That's why absolute stillness is fundamental. Inside an EUV lithography machine, the tool that prints those transistors, every mirror must stay perfectly still, within just a few nanometers. If the floor vibrates or moves even slightly, the laser misses its mark. The consequences: an entire batch of wafers, worth millions, is gone. So Samsung went to a war with the ground itself, and they've built one of the most extreme foundation systems ever built for a semiconductor fab. Every part was designed to keep the entire building perfectly still, down to the scale of atoms. They drilled more than 20,000 shafts, each about 110 feet or 35 meters deep. And they filled them with over 500,000 cubic yards of concrete. Just imagine, 5 concrete plants were built right on site just to feed that demand. That's enough material to build several skyscrapers. But this time they poured it downward instead of upward. And here every inch mattered, because a tiny vibration can wipe out months of work. Typically, a semiconductor fab uses reinforced slabs with local vibration damping under specific tools. Samsung took a different path. It turned the entire foundation into a massive floating platform. Those deep piers anchor directly into bedrock, isolating the clean room from the shifting Texas soil above. The result is a building within a building, a floating floor that absorbs every shock before it reaches chip-making tools. The result is one of the most advanced vibration control systems ever built, canceling not just tiny earthquakes, but the rumble of trucks, the hum of cooling systems, and even tremor from the Pacific Rail next door. Here they achieved not just stability, but absolute stillness. Because at 2 nanometers, even a tiny vibration is the difference between a success and a multi-million-dollar failure. And it's almost ironic because all this colossal project, massive concrete, thousands of machines, all this investment, everything goes into the building the tiniest devices on Earth. And that's because these tiny new transistors are a huge deal. Every major customer wants them. Tesla, AMD, Apple, Qualcomm, because they are not just smaller. They redefine how computation works at the atomic level. And for 70 years, transistors was the beating heart of the modern technology. But now, at 2 nanometers, that transistor itself is changing shape. And it's only the second time it happens in history. The last time it was over a decade ago, when the world moved from flat, 2-dimensional transistors to FinFETs. But now, at 2 nanometers, even FinFETs can't keep up, because at this atomic scale, electrons stop behaving like particles. They actually start to ripple and interfere like waves. So engineers had to reinvent the transistor itself, and the new radical design is called gate-all-around. Instead of one tall fin, it uses multiple horizontal nanosheets, tiny ribbons of silicon, each just a few atoms thick. And those are wrapped completely by the gate that controls them. And that's what makes this device so powerful. And if you're curious to know and see how this was invented and how right now the next generation is being developed, you must subscribe to the channel, because in the next episode we are going to the sacred place where it's all happening. The reason I'm explaining this new transistor to you, because making these devices isn't easy. It's atomic surgery. Each nanosheet has to be formed, stacked, and then aligned with angstrom-level precision. An angstrom is 1/10 of a nanometer. And the only tool capable of printing these tiny structures is EUV lithography machine. And it's happening by lasers bouncing off mirrors, polished smoother than any other surface on Earth. And if the mirror shifts by a few atoms, if the surface vibrates, the pattern fails. And the $30,000 wafer is gone. This is just to give you a feeling of how complex and sensitive the process is that Samsung is trying to pull off in the Taylor side. That's why so much engineering goes into building the fab. And that's why they need this floating foundation, to kill every possible vibration. Once the foundation was stable, the battle moved upward. TSMC was pulling ahead, and Samsung couldn't afford to fall further behind. To catch up, they had to once again reinvent how the fab is built. Normally, a chip factory takes a couple of years just to raise its frame. Samsung didn't have that luxury, so they tried something radical. Instead of pouring concrete piece by piece, they industrialized the construction itself. They turned to precast building, a method usually reserved for bridges and stadiums. Thousands of columns, beams, and slabs were made off-site and then shipped in. For a month, the Taylor site consumed the entire precast capacity of Texas. The scale of construction was staggering. Then everything arrived like an industrial Lego kit, ready to snap together in days instead of weeks. Well, it wasn't cheap, but Samsung paid this premium gladly to speed up the construction, because every month lost meant billions in delayed chip revenue. And for a moment, it worked. The walls rose in record time. But once the walls were up, they went searching for power, because a semiconductor fab burns energy like an entire city. Hundreds of megawatts, consumed 24/7. And Taylor was about to plug into one of the most unstable power grids in America. Well, if there is something riskier than printing nanometer features of transistors, that's trusting the Texas grid in winter. Texas runs on its own isolated electrical system, independent from the rest of the United States, and dangerously fragile. In 2021, a single winter storm froze the system and plugged millions into darkness. Now imagine the same grid must keep alive a factory where a single flicker of voltage for a millisecond can destroy millions of dollars in chips. So Samsung had to build its own safety net, a power grid inside the grid. They added dual high-voltage lines so fab could draw power from two independent sources. Every power source was backed up, so even if the state grid blinks, the fab would never notice. That's the madness and the genius of Taylor. When it comes to a semiconductor fab, an AI data center, or even your home, no matter how advanced the technology is, it still depends on one thing: power. And when it's gone, everything stops. Your fridge, your internet, your work. That's why I've been testing the Jackery HP 3600 Plus. It's a home backup system designed to keep your life running, even when the grid goes down. It's powerful enough to keep a family fridge running for up to 14 days. And it's ready to go in just 2 seconds during a blackout. No setup, no stress, just plug and play. And it barely loses any charge, so it's ready to go just when you need it. It also features seamless, uninterruptible power supply system, switching under 10 milliseconds, which means your computer or even medical equipment keeps running without interruption. So whether you're preparing for emergencies or just want to be more independent from the grid, the HP 3600 Plus is one of these devices that will give you the peace of mind and the real power when you need it the most. Check it out right now through the link below and save up to 65%. Once the ground was still and the power was stable, the next challenge came flowing in: water. And in semiconductor fab, water just as critical as power. If you've seen my episode on TSMC Fab 21 in Arizona, you know why. We've already explored that. So in this episode, I will be building on top of that. Inside the semiconductor factory, every wafer drinks thousands of gallons of water during its lifetime. Cleaning, rinsing, polishing, every step depends on it. In total, the factory itself consumes around 15 million gallons of water every day. It's about 5 times more than the entire city of Taylor itself. That water is non-negotiable. Without water, the entire production line stops. To meet that need, Samsung built a water factory beside the chip factory, the Blue Sky Water Reclamation Facility. It draws from Carrizo-Wilcox Aquifer, one of Texas' largest underground water systems. And it doesn't just supply water, it recycles it. Every drop that touches a wafer is then filtered, purified, and reused, with recovery rates toward 90%. It's one of the most advanced water systems in the United States, built to sustain a microchip factory that never sleeps. At first, everything worked, until Samsung upgraded the fab from 4 nanometers to 2. That's where all the problems began, because the smaller the transistor, the stricter the purity. At 2 nanometers, even a single trace of contamination can destroy an entire wafer batch. So the team now had to recalibrate every pipe, every filter, every valve to a level of precision they've never reached before. What was meant to take weeks stretched into months, and it's still ongoing today. And then the next problem was actually at first invisible. The air. Because not all air is created equally. In the Arizona desert, TSMC fights dust. In Texas, Samsung faces something else: humidity and industrial emissions. Texas air is thick and alive, heavy with water vapor, gasoline fumes, and traces of ozone. Each of these can react with delicate chemicals used to make chips. Moisture can trigger static discharge, and ozone can literally burn through the chemistry that shapes the circuit. So Samsung built one of the most advanced air filtration systems. Massive ventilation towers push air through filters so fine they can trap particles smaller than a virus. But clean isn't enough. Inside a chip factory, air itself becomes part of the manufacturing process. Every cubic inch has to be perfectly balanced: temperature, humidity, and pressure, because at 2 nanometer scale, even a single droplet can destroy billions of transistors. That's why fabs control moisture using something called dew point, the exact temperature where the water starts to condense. If it's too high, droplets form on wafers. If it's too low, static electricity builds up. So inside a fab, it's kept within a fractions of a degree, perfectly balanced between too wet and too dry. And the entire clean room is kept at slightly higher pressure than the outside world, so air only ever flows out and never flows in. Step inside, and it feels like a silent bubble. Here, the air doesn't move. It glides. This perfect filtered air flow from ceiling to the floor, sweeping away every particle before it can touch silicon. The clean room in Taylor span an area larger than 10 football fields. It's one of the cleanest and most precisely controlled environments humans have ever built. And it turns out even that isn't enough. The real magic that actually builds transistors is chemistry. And this one runs on gases: nitrogen, hydrogen, and neon. They drive the reactions that carve and coat silicon layer by layer. To supply those clean rooms, Samsung built massive on-site gas farms. This includes special air separation units that extract nitrogen and argon directly from the atmosphere, and hydrogen generators that split water into pure hydrogen gas. But gases aren't enough. Chip making runs on acids. Without it, nothing works. Sulfuric acid cleans wafer after each and every exposure step. And it has to be pure, down to 1 part per billion. And here is a wild part. Samsung Fab still imports that acid from South Korea, nearly 7,000 miles away. It's shipped across the Pacific, through US ports, and then trucked to Texas. It's expensive and absurdly complex. But until a local plant is built, there is no other option. Even the raw silicon wafers are shipped in from Japan. This fab runs on a complex supply chain, stretched across continents. Hundreds of tools arrive from Japan, Netherlands, and the US, each worth millions, each to be calibrated to atomic precision. Not every shipment arrived on time, and schedules slipped. But that wasn't the real problem. I know it's hard to believe, but all these challenges we've just discussed, concrete, power, water, air, suppliers, this was the easy part. What really makes or breaks a fab is the people who run it. Samsung flew in hundreds of engineers from Korea while hiring and training local teams across Texas. The problem is they've never built a 2-nanometer fab before, even back home in South Korea. So they didn't have this experience to bring in. At the same time, across the state, in Arizona, TSMC was building the same kind of fab, but with one key difference. They didn't start from zero. TSMC first perfected the 2-nanometer manufacturing process at their main mother fab in Taiwan, where every tool, every parameter, and every step was already mastered. And only then did they bring that experience and those people to Arizona. This means TSMC started from experience. Meanwhile, Samsung had to reinvent everything. A new process in a new country with a new workforce. So the factory was almost complete, but it never truly came alive. Because running these multi-million-dollar machines isn't about default settings. It's about coordination, intuition, and trust. And those are the things you can't import or rush. And that's where the big difference between TSMC's Fab 21 in Arizona and Samsung Taylor Fab begins. TSMC spent over 40 years mastering one thing: building chips for others. Every engineer, supplier, and process serves a single goal: yield. Yield is the percentage of working chips per wafer. And at 90% that TSMC achieves, you're practically printing money. Samsung, on the other hand, fights too many battles: designing phones, building displays, and making memory, while trying to run a foundry for others. And that lack of focus costs them a lot. Because the moment you compete with your customers, you lose them. And TSMC in Arizona had Apple as a customer from the day one, and that gave them rhythm and stability. Samsung had none, no stable flow of wafers to tune the process. That's why today TSMC's Arizona fab is already shipping 4-nanometer chips and ramping up the production of 2 nanometers, while Taylor is not exactly producing any hits. Because in chip making, you can copy the walls from one continent to another, but you can't simply copy the recipe. Every fab uses roughly the same machines, but each runs on its own secret combination of timings, chemistries, and pressures that define the quality of every transistor. Those recipes are the true intellectual property of chip making, guarded like national secrets. And here is TSMC's unbeatable loop. The world's top customers, Apple, Nvidia, AMD, Qualcomm, all trust TSMC. That trust brings more data and revenue, and that revenue funds R&D. And R&D improves the process. And better processes attract even more customers. And even if someone would try to copy this recipe, it wouldn't work from scratch, because no two fabs are identical. Air is different, Water is different, vibrations are different, and people and culture is also different. A process that works flawlessly in Taiwan or Arizona can take many years to recalibrate in Texas. As you can see, it looked like the story was over for Samsung in Taylor. Despite all this engineering brilliance and perseverance, they couldn't get it right. And then, when everything seemed lost, Tesla stepped in. Tesla signed a $16.5 billion deal running through 2033. And Samsung is committed to manufacture its next generation AI6 chip right here in Texas. For the engineers in Taylor, it was a spark of redemption. Tesla's new AI6 chip will power entire Tesla ecosystem, including Tesla full self-driving system, Optimus humanoid robots, and AI training clusters. It's expected to be 2 to 3 times faster than Tesla's current AI5 chip. And this single chip will replace dual chip design used today. And this time, Samsung offered something new: exclusivity. And for Tesla, this decision was strategic. Tesla wanted a dedicated line, a factory that could focus on their design, without fighting Apple or Nvidia for priority. They wanted control, to send their engineers into clean room, to co-design and tweak parameters in real time. And they wanted proximity. And Taylor sits literally half an hour away from Tesla's Austin headquarters, so Elon Musk could literally walk the line. Samsung offered something TSMC couldn't: exclusivity and local production. In return, Samsung got what it desperately needed: an anchor customer, a reason to finally turn the machines on. The production of AI6 is now expected by 2028, ramping to full capacity by 2030. Just as Tesla scales robotaxis and humanoid robots. That's when the fab will start making money. And it will take them quite some time to recover their investment. For Samsung, it's a lifeline. For Tesla, still a risky gamble. Because if yields fail, this partnership could collapse before it begins. Because Tesla chips demand just the same high yield, or the whole economics collapse. Taylor was meant to be the next chapter in America's chip comeback. Proof that US can match Asia's precision. Instead, it became a huge warning. Even if you have billions to spend, you can't simply copy this excellence. And at the same time, it's a glimpse of how far ahead TSMC is, and how much of our technological future still depends on them. TSMC currently leads both Intel and Samsung in advanced semiconductor manufacturing, dominating cutting-edge nodes like 4 nanometers, 2 nanometers, and ramping up soon 1.6 nanometer class technology. It's 2 nanometer process entering mass production right now, and their next 1.6 nanometer processors are planned for 2027. And this will push chipmaking into the angstrom era. And in many ways, Samsung's story mirrors Intel's. Both led chipmaking, and both lost their edge trying to do too many things at once. They both faced delays in next-generation nodes, struggled to win external customers, and watched competitors outpace them despite massive investments. And it looks like the core problem is structural. Considering Samsung engineering culture, I'm pretty sure they will manage to turn Taylor into success, even though the road there is way harder than anyone ever expected. Now, if you want to know what it takes to build the world's largest AI data center, Make sure to watch this episode right now. You will love it. And I will see you there. Ciao.